A very good day to Dr. Sakir. Today my teammates and I are going to present about the RF technique and microwave assignment. So let's move on to the objectives. The first objective is to understand the theory of microwave passive filter using insertion loss methods. And second was to design the lumped and distribution of low-pass and band-pass filter. And third objective is to evaluate the transmission line circuit for of RF system. And let's move on to the introduction for low-pass filter. A low-pass filter allows a signal with frequency below a certain threshold called the cutoff or center frequency to pass through while attenuating higher frequency. It's often used for noise reduction and signal conditioning. This filter's bandwidth controls how many frequency it can pass, and insertion loss tells how much signal power is lost during the filtering. Low-pass filters are widely used in audio or communication or many other electronic systems. Secondly is for band-pass filter. A band-pass filter only allows signal with specific frequency range to pass and block those outside this range. It's combined a low-pass and high-pass filter. The center frequency is where signal transmission is strongest, and the bandwidth defines the range frequency that can pass. Insertion loss is also crucial as it impacts signal quality. Band-pass filter are essentially in application like radio receiver where only a narrow frequency band is needed. Third, we're going to see about the application of filter. Filter have a wide range of practical application. In radio, band-pass filter are used to select specific station. Low-pass filter are used in noise suppressions, anti-aliasing to remove unwanted high-frequency components. Audio system use both low-pass and high-pass filter to manage bass and treble output. This filter separate frequency component to enhance sound clarity and are crucial in electronics and audio processing and communication system.
In this slide, I'm presenting the initial design stage for a lump low-pass filter. So the given design specification include all cutoff frequency, which is 2.5 GHz, and insertion loss is 35 dB, and ripple is 3 dB equal rip, and the frequency is 3.5 GHz. First, I calculate the normalized frequency ratio using the given frequencies, so resulting in a value of 0.4. This value is used with standard filter design chart shown in the slide to determine the required filter order. By locating the intersection point for the calculated frequency ratio desired attenuation, it is clear from the graph that the appropriate filter order is 6. So this is confirmed by referring to the 3 dB ripple prototype element values table, which provide a normalized element value needed for a further circuit synthesis. So therefore, the filter order is lump low-pass filter is determined to be 6. Okay, now I'm explaining how I calculated the component values for the 6th order lump low-pass filter. So this is the element value for N6, so which is G1 to G7. Why until G7? Because for 3 dB ripple, we must take all the values. So now, the middle section, which is the method, I choose the T combination because this configuration is commonly used for even order filters because they provide a practical way to implement the required series inductors and shunt capacitors. So the equation provided show how the inductance and capacitance values are derived using a normalized coefficients. So on the right, I have shown the step-by-step calculation for each component resulting in the physical values needed for implementation. So these values include inductors ranging from 11.2 Nh to 18.49 Nh, and the capacitor value is 0.78 pF to 0.768 pF. So which will be used to build the filter circuit according to the desired specifications. Okay, now I'm explaining about the distributed design for Discharge transformation. So the inductance became a short circuit and the capacitor became open circuit. For G1, which is inductance, it became a short circuit, and for G2, capacitance became open circuit, and G3, inductance became short circuit, and the G4, which is capacitance, became open circuit, and G5 became short circuit, and G6 became open circuit, and the last one is G7, which is inductance, became short circuit. Okay, the first schematic shows the initial discharge transform filter with open and short circuit stub arranged as a derived layer. So the box section, eyelet section that are difficult to realize directly. So I changed the short circuit to open circuit, and the last also same, the highlight box which is a short circuit, I changed to open circuit. So this is the result how the short circuit became open circuit. So these four highlight box I want to change, which is open circuit to short circuit. So the final practical layer of after all Corona transformation have been applied, here all elements are irrealizable, shunt configuration, and impedance inverter as scaling factors. So as a N2 used to maintain the same filter response while ensuring all sections have practical line width and specific spacings. So this approach makes the distributed low-pass filter design practical for implementation on a microstrip or stippling circuit while maintaining the desired frequency response characteristic. Okay, in this slide, the final distributed low-pass filter design using Corona ADB is fully converted into a realizable microstrip or transmission line layout. So the first diagram shows the final network after the Discharge transformation, and Corona steps have been applied. So each number at the top represents the normalized impedance ratio for each section, while the number at the bottom corresponds to the normalized admittance or impedance of the stubs. So this layout shows how the filter now consists entirely for shunt stubs connected to the main transmission line, which makes the performance predictable at high frequencies. So below is I times with the 50. So the bottom diagram show the actual characteristic impedance in ohms for each transformer line a section. So the main line start and ends with the 50 ohm standard input and output impedance, which is 1 times 50. So the shunt stub have characteristic impedance ranging from moderate values to very high values, which is 497.5 or 610, which correspond to narrow or wide microstrip lines when implemented to the PCB. Okay, in this slide, I'm showing the final distributed filter layout using Corridor identities ready for practical implementation as a microstrip filter. So the diagram illustrates the complete physical structure of the filter. It starts from port 1 on the left and end at the port 1 RF out. So on the right, the main transformation line a section with different characteristic impedance starting and ending with a standard which is 50 ohm lines for easy matching to other RF components or measurement equipments. So each section in the main line is connected to the shunt stubs, which is a vertical line that act as a capacitive or inductive elements originally specified in the lump prototype. So the characteristic impedance value of the stubs are given below each stub. For example, 140, 31.3, 301, 63, 610, 31, and 142.6. And the main line segments have a corresponding impedance, which is 78.1, 72.15, 405.5, 497.5, 90, and 77. So all stubs are quarter wave, which is 45-degree length, and open or short circuit at the end according to the Richard and Corridor transformation. So the entire layout ensures the same filter performance as the original lump design, but using only practical transmission line. Okay, on the left side, you can see the complete circuit schematic that I built in the simulation software, which is ADS. So it shows the 6-order lump element filter consisting of 4 inductors and 3 capacitors connected in the T-network configuration that I calculated earlier. So the component values match the value I derived. So the inductor range is 11.2 Nh to 18.49 Nh, and the capacitor range is 0.768 to 1.01 PF. So the input and output ports are matched with 55 termination. So on the right side is the simulation result show as the S parameter versus frequency. This plot shows how much signal passes through the filter at different frequency. From the graph, you can see the filter achieve the expected performance. It allows signals up to the cutoff frequency of 2.5 GHz. Then it sharply attenuates signal above this frequency. The markers show the cutoff region where the insertion loss started to increase significantly, matching the theoretical design target. So the result confirmed the lump element values and the filter topology successfully achieved the desired low pass behavior and the specific cutoff frequency and ripple. Overall, this verified the design before moving on the implement in the distributed form. Now we can see the complete distributed filter schematic built in ADS. So the filter is implemented entirely with transmission line sections, each having the specific characteristic impedance and electrical length that were calculated and transformed using Corridor identities. So the open or short circuit stubs replace the lump capacitance and inductors from the original design. So on the right side, the flow showed 2S to 1 response for distributed filter dB versus frequency. So the result demonstrates the filter achieved the low pass behavior with the cutoff frequency around 2.5 GHz, matching the target of lump prototype. The measured insertion loss at cutoff is about 3.3 dB, which is consistent with the 3 dB ripple design. Behind the cutoff, the signal attenuated sharply, confirming the filter performance. So at the bottom, the layout view shows the physical PCB layout of the distributed filter. So this is how the design will look when fabricated on a microstrip substrate. You can see the main transmission line with multiple branches, shunt stub connected along it. So each line section corresponded to the impedance value and length from the schematic. So this layout ensures the practical filter work as a design at a microwave frequency. So overall, the slide show the lump element filter has been successfully transformed into a practical distributed filter using Corridor method and verified by the both schematic simulation and layout design.
And son of tester. My name is Nur Inshira Dijani, B08221044. So here this is my part. I would like to present about what is bandpass filter. So bandpass filter is an electrical circuit that enables vertical frequency pass band to pass through while attenuation frequency outside range. Stop band. The filter combines a low pass filter and a high pass filter. When building a microwave bandpass filter, it is important to evaluate the relevance of each parameter and its impact on performance. The center frequency is the frequency at which the filter has the highest transmission and lowest attenuation. The center frequency is set to the frequency range for which the filter can pass signal. It is necessary to separate or extract a certain frequency component from a signal. The bandwidth of a filter refers to the frequency range where it functions well, often between -3 dB attenuation and the center frequency. The filter bandwidth determines the frequency it can pass, in fact, the capacity to transmit desirable signal while alternating unwanted ones. A filter with a bigger bandwidth may pass a wider variety of frequency. Essential loss refers to the loss of signal strength during filtering and is often measured in decibel. Essential loss directly impacts system performance and signal quality. Lower essential loss indicate better transmission efficiency, while larger essential loss can lead to a signal degradation and less sensitivity. So, application of filter. Tunnel in radio, which use bandpass filter that allows a fixed frequency to the speaker. Noise separation, which used for noise removal from the received signal. Anti-aliasing, which use low pass filter to filter out high frequency component to prevent aliasing component from being sampled. Treble and bass of a speaker, which use low frequency for bass and high frequency for treble. They are separated and routed using high and low pass filter to produce clear music. hosting film lumped elements for integrated circuit and inductor capacitor for microcircuit and board application. It also involves lumped element design, distributed element design. An electronic filter with a distributed element design does not contain discrete component for capacitance, inductance, and resistance. Lumped element filter have two, which is T-network design use series element, while pi-network design use shunt element. T-network is recommended for each order filter, while pi-network is for odd order filter. To determine capacitance and inductance value of filter, lumped elements value must be determined. There are two methods, which are image parameter method and insertion loss method. So in here, um, in this slide here, this is a graph of a bandpass filter. So in the information, cutoff frequency is 2.5 GHz, ripple is 3 dB, and 5 bandwidth is 260 MHz. So we plug all of this information into the formula. So the frequency 1 is equal to 2.5 GHz minus 260 MHz divided by 2 equal to 2.4, and frequency 2 is 2.5 GHz plus 260 MHz divided by 2 equal to 2.6, and the omega O is 2 pi times frequency cutoff, which is 2 times 2.5 GHz equal to 5 GHz, and for the theta is omega 1 minus omega 2 divided by omega O. So the answer for theta is 0.251. So as given in our task group, we got N5. So how to find the value of G1 under G5? So you can identify the value of G1 under G5 as in the table. The table is fixed and you can find the table in the internet. So our N is 5. So here you can see, so N5, so from G1 until G5. So the value is 3.4817, 0.7618, and 4.5381, 0.7618, and G5 is 3.4817. So on this slide, I will present the fundamental equation used to determine the values of the individual components. Which in our filter design, this formula allows us to translate desired filter characteristic into tangible component value. So the formula for CK is CK equal to which is TK divided by theta times RO times omega O. So breaking down the first formula, CK represents the capacitance value for the K stage of the filter. Refers to the K element of the low pass prototype filter, which are normalized value obtained from filter table like Butterworth or Chepsey. So theta RO is the impedance scaling factor, often representing the impedance transformation between sections or a characteristic impedance. Omega O is the angular resonant frequency or the cutoff frequency of the filter, expressed in radians per second, or you could say angular cutoff or center frequency. So it's depending on the filter type. So breaking down the second formula is LK, which is theta times RO divided by GK times omega O. LK represents the inductance value for the K stage of the filter. Similar to CK, GK is the K element of the low pass prototype filter. So theta RO is again the impedance scaling factor. Omega O is the angular resonant or cutoff frequency. As you can see, we have two important formulas here. So the first formula show is CK equal to theta divided by GK times RO times omega O. So CK represents the capacitance, the term GK RO, and omega O are crucial parameters derived from our filter specification representing prototype value, characteristic impedance, and angular frequency respectively. So this is a formula for series inductor. So the LK is, which is GK times RO divided by theta times omega O. This formula allows us to determine the inductance value for the corresponding filter stage. Again, GK refers to our prototype value, RO is the characteristic impedance, and theta omega O represents the bandwidth of frequency range of interest. These equations are fundamental for translating our theoretical filter design into practical. Realizable circuit will be using this in our assignment to determine the specific component value needed for given filter requirement. This slide shows the manual calculation for the inductor and capacitor used in our 5-order bandpass filter design. On the left, we have value for the shunt components L1, L3, L5, and their corresponding capacitor C1, C3, C5. These were calculated using standard formula involving normalized element values and filter specification. On the right are the series component L2, L4, and capacitor C2, C, and 4. Each value was derived based on the center frequency of 2.5 GHz and the bandwidth of 600 MHz. This calculation ensured that our lumped design matched the desired filter response before simulation. Here is the schematic of our lumped element bandpass filter design using Advanced Design System ADS. The filter is designed for a center frequency of 2.5 GHz with a 3 dB equal ripple and 5-order filter. The circuit consists of series inductor and parallel LC resonator. With carefully calculated value, meet the requirement bandwidth of 260 MHz. On the right is the S parameter simulation result. So, the marker M2, the center frequency at 2.503 GHz, the 3 dB points M1 and M3 are at approximately 1.91 GHz and 3.00 GHz, indicating the desired bandwidth is achieved. The insertion loss is minimal at the center, and the filter response shows a sharp roll-off, which matches our design goals.
This project involves designing both low-pass and bandpass filter using lumped and distributed methods. The Chibishu low-pass filter provides a sharper roll-off, but also introduce some pass-band ripple. To build practical microwave filter, we converted the lumped component into microstrip base, designed using rigid transformation, and further identifies, however, challenges across such as high impedance and impedance value that are difficult to fabricate. For bandpass filter, we have used frequency transformation to center it at 2.5 GHz, and stimulation show good performance using ADS software. From this project, we can conclude that this project met its goal by designing and analysis microwave filter using professional tools and proven techniques. We gained deep insight into RF filter theory and practical skills in layout and simulation. The Chibishu filter were effective, and the distribute microscope implementation taught us the challenges of real-world fabrications. Using the ADS, we verify our design and handle issues like impedance limitations. This experience has greatly enhanced our knowledge and readiness of our future work in high frequencies, electronics, and telecommunications.